All right. Let me just post the link over to Leetcode's Reddit so I can get so I can alert people. Leetcode. Awesome. All right. So this is question 1485. Clone a binary tree with a random pointer. This question seems to be a similar question to the clone a linked list with a random pointer, except in this case the data structure is just a little bit different. It's a binary tree instead of a linked list. But if you remember back from the linked list version of this question, it was basically just storing the mapping between the old linked list nodes to a new linked list node inside of a hash map. Now this one's going to be similar, but we'll see. So first of all, without the whole random pointer, we have to create a clone of the binary tree. So let's take away the random pointer for a second and ask ourselves, how would you clone a random binary tree? How would you clone a binary tree just generally? How would you clone a binary tree? I would do it personally. There are a lot of ways to do it. I would just use breadth first search, because the algorithm for that is super easy. So let me just start writing some notes here. So I would use breadth first search to clone. Now, obviously, the trick with this question isn't just cloning, it's the fact that each node has a random pointer in it. So, this node, the root node, has a random pointer to null. Maybe the 4 has a random pointer to what happens to be its child, but it didn't have to be. For example, the 4 could have had its random pointer point back up to its parent if it wanted to. Or the 4 could have had its random pointer point to null if it wanted to. So, or it could have had a random pointer point to some random other node inside of a larger tree if it wanted to. So basically we need to keep track of these random pointers. So the way the breadth first search works though is you would, every time you get to a node, you would clone all of its children. You would clone all of its children, and then you would put the children onto a stack. Not the cloned children, but the original children. You would put the original children onto a stack, or a queue actually, since it's depth first search. So you put all the cloned children onto a queue, and then you would simply keep popping off from that queue and keep doing the same thing where you put all the children into a stack or a queue, and you keep doing that until the queue is empty. That's depth first search. So first of all, let me just implement the depth first search part so we can get that out of the way. I wouldn't do it this way in real life. In real life, I would do the whole problem all at once, but just for demonstrative purposes, let me clone the depth first search part. So right now, imagine there's no problem, there's no issue of there's this random node that you need to clone, and let's imagine that it was just a normal binary search tree or a binary tree with left and right nodes. There's no random node. Just imagine that. So let's get that done out of the way. So let's just clone a regular binary tree using depth first search. So like I said, you're going to need a queue, and this queue is going to hold all the nodes that you haven't visited yet. And then you're also going to need a list of mappings from old to new, right? So I'm just going to call it scene. It's going to be a dictionary, and what this is going to do is going to map old nodes to new nodes. So what this means is that for every old node we see in here, which, the original, so I'm going to call it the old nodes. So for every single old node, we should have it map to its new node inside of the new tree. Okay, and first of all, I'm going to create a a new root. So new root is equal to, and I'm going to create a node object. And in this case, in this case, the values I'm going to pass in are going to be the original root node's values. So root.val. I need to copy that root.val. But I also need to clone the children, but I'm not going to do that yet. I'm going to leave it like this. And right now, the left child, the right child, and the random node are all none. And we're going to leave it like that. Because what I'm going to do later is I'm going to pull from this, and I'm going to, in a sec, show you how to clone the generalized case of a binary tree without worrying about the random node. So yeah, like I said, breadth first search, you need a current old, which is going to be the root node, and you also need a current new. And let's set that equal to the new root. Now we need to keep this variable new root separate, because this is actually what we're going to return at the very end, right? We need this reference to the root of the new tree, because we're going to return that at the very end. And then finally, we need to add to our queue, append to our queue, the current old. So while the queue is not empty, we need to pop from the queue. So let's just say our current old is going to equal to queue.pop, and let's say pop 0 because we want the first element, not the last element. If we did pop without the 0 in it, that would actually pop the last element, which would turn this into a stack. So anyway, we have the current old is equal to queue.pop 0, so we get the first element. And now we have to figure out what we do when we get a brand new old node. So now we're at an old node. We need to go through its children and add those children, create a whole new node for those children, and add those children to the new version of the node that we're at right now, right? So for every, well, in this case, there's only left and right. So let's create a brand new left and right. So if current old dot left, so if that exists, then we need to create a brand new node for it. So let's say new left, let's call it a new left, is equal to a new node with the current old's left value. And we want to map that new node, or we want to be able to get that new node inside of the map. Yeah. And we want to be able to get that new node inside of the map. So we'll just say scene at current old dot left is equal to new left. And then at this point, we basically have a mapping between the scene.currentOld. So current old.left, its left child, which in this case doesn't exist. But let's just take, for example, this for its left child has now been cloned, and in the new version of the tree, the copied version of this tree, this copy corresponds to the correct new version of the 7 node. But we still haven't made the copied 4's child equal to that 7 node. So we need to do that still. Right? So whenever we pop from the queue, we need to get that current new. Because we got that current old, let's imagine that current old is 4 in this case. We need to get the corresponding current new. And that's why we create the whole map in the first place. So the first thing we do after we get a new node from the queue, which is, imagine we get the 4 from the queue, the first thing we do is find the equivalent of that 4 inside of the new binary tree. And that's what we're doing in this line. So current new is equal to seen at current old. We found the equivalence of that for inside of the new binary search tree. And now we say if current old dot left, if that exists basically, then what we want to do is create a whole new node, create a copy of this 7 node. We want to map this old 7 node to that new 7 node so that we can do this step later on. But we also need to make sure that the current new, which is that 4 in the new version of that 4, its left child is equal to the new left that we just created, that 7 copy that we just created. Awesome. Else, if current old dot left doesn't exist, if it doesn't exist, then we need to make current new dot left equal to none. Although it should already be none, but let's just make that explicit. One more thing. Whenever we create a new node, like a 7, we need to add the old node to the stack because it needs to be explored because maybe that 7 had children. So we need to add the old 7, the original 7, to the queue because that still needs to be explored. So the last thing we need to do is queue.append current old.left, that child. And like I said, it's just because it needs to be later explored. So now that we added it to the queue, eventually we will get to that 7 and we will explore its children. That's how we make sure we explore its children. Okay. And essentially the same exact thing needs to be done for the right. Right, so if the right exists, so in this case we're looking at this one, if the right exists, then we need to basically do the same thing we did up here. Create a new right. So the current old's right value, which is 4 in this case, we need to create a copy of that. We need to make sure we update our dictionary or our map, which maps the current old.right node to the new right node. And we also need to make sure that our current new dot right is equal to that new right node that we just created. And finally, we need to add this old node to the queue. We need to add this 4 to the queue so that it will get explored. Its children will get explored as well. Finally, just to make things extremely clear, if the current old's, which in this case is 1, if that current old's right doesn't exist, then you just make the new or the copied version of the 1 make its right a null as well. For example, the copied version of the 4, its right node will also be null. Great. So this actually will just clone the entire binary search tree in the case where you only have a left and right node to worry about. And this is how it would be done. This is just a breadth first search using a queue. And this is how it would be done using a map as well. Obviously though, this problem isn't that simple. We have the idea of a random pointer, which makes things a little bit more complicated. So let's look at this example because I think it illustrates the complication a little bit better. Because there's there's a case in here that is really important. Because when we're talking about random pointers, there are 2 situations that you could run into. The first situation is you run into a random pointer and it points to a node that you've already seen, that you've already created a copy for. Or you run into a random pointer that points to a node that you haven't already seen, that you haven't already made a copy for, right? So those are 2 different situations. Why? Well, in the case where you've already created that copy before, you don't want to create a whole new copy then your graph wouldn't actually look like it's supposed to. And in the case where you do copy, where you haven't seen it before and you create a copy, you need to make sure that your future basically algorithm can remember that you created already this copy. And let's say, for example, you're at the 1, its random node, it points to the 7. Okay? You don't want to wait until breadth first search gets to the 7 and somehow remember that you needed to have pointed the random node from the very first root node all the way to 7. You don't want to have to do that. That's complicated. Instead, what you do is whenever you see a random node that you haven't seen before, whenever you have a pointer to a random node that you haven't seen before, create it now. Just create it now. So actually, the very first step, what you should do is you should create a copy of the root node, and then in the very first step, create a copy of this 7, and say the random from this root node points to the 7 node. Okay? And now that you have that done, eventually you're going to get to this 3. And this 3's right node is going to point to the 7 as well. So how do you remember that you already created that 7? And how do you retrieve that 7 such that instead of creating a whole other copy of this 7, you can just make the new 3 point to the copy of that 7 that you created way in the beginning? Well, obviously this question, like I said, is very similar to the linked list version of this question, where you can just do this using a hash map. So if I create a hash map for matching, which I've already kind of done really, matching old nodes to new nodes, I can ask myself, okay, I'm at this node right here. Have I seen the equivalent of, so this node points to this random 7. This is the old 7. Have I seen this old 7? So I need to map old nodes to new nodes, which I'm already doing basically that, right? This is a map from old node to new nodes. So when I'm at this 1 node and I see the 7, because this random pointer points to this 7 node, I have to ask myself, have I seen the 7? And I can ask myself using that map that I'm creating. And if I have not seen that 7, then I create it and I add it to the map. I add this node mapping to that 7, to that new 7. And that way, when I get to this 3, before I immediately create the 7, assuming that it wasn't already created, before I create it, I can say, okay, give me 3's right node. In this case, it happens to be 7. Before I create the 7, I ask myself, is that 7 inside of the dictionary? Because if it is inside of the dictionary, then all I need to do is point the copied version of this 3's right node to that copied version of the already existing 7. So I don't really need to do much except number 1, whenever I explore a new node, I need to add its random pointer. And if that node doesn't already exist, that random node doesn't already exist, I need to create it and add the mapping from the old node to the new node in the hash map. And number 2, before I ever create a node due to a left or a right, before I ever create a node, I need to make sure it hasn't already been created. So let's go back to the code. So the first part that I was talking about, which is creating that random node whenever I see it, that can be done here. Let's just do that here. So let's say I pop from the queue, I find the corresponding new node inside of the new binary tree for that. So let's say I start with this root node. I pop from this queue, which had that root node in it. I found the corresponding new root node, which I created up here in the starter code. And now I'm ready to look at the random pointer for this. Okay. So if the current old dot random, so if that random pointer does exist, and let me just already say that if that random pointer doesn't exist, then the current news random pointer is just going to stay none. Now I don't have to write this because it gets initialized to none in the very beginning. That random gets initialized to none in the very beginning. But I just like to be clear about it, that if the current old, which in this case is this one node, if its random pointer doesn't exist, or if it points to null is basically what I'm saying, then I got to make sure that the new version, the copied version of this, its random pointer also points to null. But in this case, it doesn't point to null. So what I do when it doesn't point to null, well, first I need to see if it's already been created. Because you also have to remember, another complication is that maybe two nodes' random pointers will point to the same node. That's another thing. So, just because, so basically what I'm saying is that you always have to check to make sure that it wasn't already created. Okay, so now I have to check, is the random node already created? So if current old dot random, that gets the random node. In the very first case, it'll be the 7 node. If that is already created, which means if that is inside of the scene dictionary, then it means it's already been created, right? If it's already been created, the 7 has already been created somehow, then I need to map that new node, that new one, it's random, to the already created 7 copy. So current new dot random is going to be equal to that already created 7 copy, which I get from the dictionary. Boom. So what happens if I haven't already seen it? Well, I need to create it. We've already been over the fact that if you haven't seen that 7, then you need to create it. And you need to put it inside of the dictionary so that it can be looked up later. So current, well, you need to create a brand new random. So I'm just going to call it new random. Is going to be equal to a whole new node with the current old's random node's value as the parameter. So it gets created with that value. I need to make sure I map the current old dot random, which in this case would be 7. I need to map that to the new 7, so that cloned copy of 7, which I just created right now above it, which is new random. Okay, and I also need to set the copied versions of this. So current new dot random is equal to new random. Now, yeah, I could have taken this part outside, because if I had replaced this part with this right here, it would have worked just as fine if I had made sure I added it to the dictionary before I executed this line. But this is clear enough, so we'll leave it like this for now. So I hope you understand what's going on here. Basically, whenever I see a node, whenever I'm exploring a node, I look at its random pointer. I look at the node that it points to, the random node that it points to, in this case it's 7, and I ask myself, have I seen that 7 before? If I have seen that 7 before, then that means its clone exists. But how do I find that a clone? Well, that is through the dictionary. So I get that clone, and then I get the clone of 1, and I make sure the clone of 1's random pointer points to the clone of 7. And that's basically all I'm doing. And if that 7 clone doesn't exist, then I create it. Okay. One more thing is that whenever you do this, you have to make sure that whenever you're checking the left and the right, and you're going to create it, you always have to make sure that you didn't already create the left and the right. So if current old dot left, all this that I'm doing right here only has to be done if current old dot left is not in the scene dictionary. And same thing for the right. Right, so if it's not in the scene dictionary, then I need to create it and everything, like I was doing earlier. But if it already is in the scene dictionary, then for both of these cases, I can just link them up. I can link up the current news dot left and set that equal to the scene at current old dot left. And same thing down here. Right. Yeah, so if it already exists, then I don't really need to create it. I just need to link them up. So for example, if this one, its right child is 3. But if for some reason this 3 was already created, because, you know, random pointers and stuff like that, then instead of creating a whole new 3 copied, I just need to make sure that the 1's copy points to the 3 copy. And that's basically what I'm doing here. And finally, after I'm done with all of this, I need to return the new roots. Now, the question of should I add the current old to the stack at this point if it already existed? So for example, I see 1, I go to 3, it already exists. Should I still add 3 to the stack? Well, yes, because 3 hasn't been explored yet. It's just been created. So I still need to add it to the stack in this case, in these cases. So for both of these, I need to queue and of course I could have just taken this line out, but like I said, I would have done this a lot differently if it was a real interview. I wouldn't have done it in separate steps. Like I wouldn't have done breadth first search and then implemented the random points. I would have just done it all in one go anyway. But this is just trying to be clear, you know, get the whole like thought process done. Cool. So usually there's always an error. Let's see here. Current new is equal to seen at current old. Oh, I haven't added it yet. Not a node copy instance. Well, the reason that it's giving me this error is because in the instructions, it says I need your class. You'll be given a tree in class node, and you should return the clone tree in class node copy. Node copy is just a clone of node class with the same attributes and constructors. But I assumed for some reason that that wasn't going to be the case anymore, just because I didn't really see a reason for that, and I totally forgot about it. But my bad. I don't see like why they would want me to create a whole new class. Literally, just there's really no reason at all. Okay, so. Yeah, see, I didn't read this part here, that they were really expecting a node copy class. So now I have to go to do every single one of these and call it node copy. Oh, this is dumb. So I got node copy here. I got node copy there. Why isn't these highlighted? Why aren't these highlighted? Okay, got node copy, node copy. Let me try. Cool. Before I submit though, sometimes I'm guilty of submitting things without considering the edge cases because I get so used to Leetcode just telling me that I got the edge cases wrong instead of, you know, in real interviews, they're not going to tell you got the edge cases wrong. You have to come up with the edge cases yourself. So let me spend some time doing that. So let me think about this. So what would be some edge cases? So if I'm given, for example, something with, let's see, just one node. Let's see what happens. Actually, I'm not sure. Let me visualize this. Oh. Oops. So it's 1, 4. Oh, 1 comma. What's that supposed to be? The 4 and the 3. Oh, index 3, as in 0, 1, 2, 3. It goes to 7. Okay, then let's just take out. Let's just make this null. And let's take this out. I should do it. Yep. This is the case where it's just these two. Okay. And then another one. Let's do another one where, so this points to null. And let's take out this one. I think that's good. Okay. So let me submit. Oh. Hold up. Let me go back to here. How do I, take away the tree visualizer. So it says none type. Object has no attribute val. So where it says new root, node copy root.val, that means that I was either able to get something from the dictionary that, well, let me actually go to the line so I can show you what I'm talking about. So right here. So new root. Oh, this is given to me when root doesn't exist. So I don't even know what to return. I'm just gonna return none. What happens if I take away literally everything? Is this a valid tree? Is that a valid tree? See, I always fall. Oh my god, I'm so tired of falling forgetting about that. Forgetting about the absolute zero input. Cool. So it says 256 milliseconds faster than 82% of Python 3 submissions. 18.4 megabytes less than 66% of Python 3 submissions. So not terrible for my first time solving this question. Let's see what other people did. Simple single pass depth first search with the hat map, literally what I did, and this one's in Java. Java hash map, recursive and iterative. I don't know why anyone would do it recursively, but I guess maybe they want to see what it looks like. They did a copy random binary tree. They did breadth first search or depth first search. It depends on the pop. They pop at the very end, so that means it's depth first search, which is cool too. As long as you get all of the nodes. Cool. Let me check YouTube. How do I check YouTube? Let's see here. Awesome. Cool. So that was actually not that bad. I have to eat dinner now though, so I have to go. But when I come back, probably tomorrow, I will solve another Leetcode question. So I'm trying to do one a day. It's not that I'm looking for a new job or anything. I just want to make sure I keep this skill up because I really enjoy it. So yeah,